You don't want to sit in the front row. So, welcome back. Speaker is Felix Stutz, complete multi-party session type projection with automata. Go ahead, Felix.
Thank you, Simon. Yeah, so I'm Felix Stutz from Max Planck Institute for Software Systems, and this is joint work with Elaine Lee and Thomas Wies from New York University, as well as Damien Zufferey from Source. So we've all seen today that this should work, and it does, but with some delay, I'm sorry. So in this talk, I will represent global types in this visual fashion because I usually do in presentations. I expected here you would have understood all the syntax, but in some audiences they don't. So this is a global type which represents a load balancing protocol represented as high-level message sequence chart. We start at the top. There's a client C who sends a task to the server, and then the server distributes the task to one of two workers, either the worker W in the left branch or the worker U in the right branch, and then it sends the result right back to the client, and then it recurses. You've all seen something like this. I just want to give you this idea. Okay, we're in this model, multi-party session types. We take a global object and we want to produce a local object. And how do we do this? Usually it's projection, right? And here, I depict projections as finite state machines. So this is the local specification for the client C, where it starts at the top, S!T. I don't need to tell you, that means that C sends the task T to the server S, and then it receives the result either from the worker W or the worker U, and for conciseness, I didn't merge these states for readability, basically. So let me be a bit more specific about the model for our local specifications or local implementations. As Marco pointed out, we actually do not use local types, but we use communicating state machines, which are a standard model for distributed computing. So introduced by Brandt and Zufferey 40 years back. And we do so with channels, so we are in an asynchronous message passing setting. To be precise, the programs or the specifications are finite state machines rather than push-down automata or even Turing machines. And our channels are point-to-point, so a participant can decide to send a message to exactly one participant rather than just broadcasting it over the channels. Capacity is in theory unbounded. We consider reliable channels, so no lossiness or anything like that. And the order between, like for every of these channels, which is like one between each two participants for each direction, is FIFO ordered. Okay. Interestingly, this model is known to be Turing complete as established 40 years back. So what we consider in this paper is what we call the implementability problem. Given a global type, can we generate a deadlock-free communicating state machine with the same language? So it generates exactly what we wanted to specify with our global type. And for this particular example, we can generate the local specifications similarly as I've shown before for the client, also for the server and the two workers. And this indeed is a deadlock-free communicating state machine that generates the same language. However, we all know that things can also go wrong. You cannot just take the projection and let them interact because they might either generate more or they could deadlock. So here, the reason for this is that in a multi-party setting, every participant only has this local view of what it knows of the global run of the protocol. So we have three participants, A, B, and C. A decides the branch to take, either left or right, by sending an orange or a purple message. But then B doesn't forward this information properly to C. It just sends a blue message in both branches, but C later should know which branch was taken. It's easily observable that this cannot be implemented because C will never know which branch was taken from the local view it has. So we can obtain a candidate implementation that looks like this. And here you see that C basically receives a blue message but then branches, and this is where you get into trouble, and this candidate implementation, and in fact any candidate implementation, will exhibit this behavior, where the participants A and B took the left branch and C arbitrarily decided to take the right branch. So from an algorithmic point of view, we would like to distinguish between these implementable global types and unimplementable global types, like this one. And I want to depict this space of multi-party session types, or rather global types, with a blue box, and then in this there is this implementable blob. And this particular, like here for us, this means it's implementable if there is such a deadlock-free communicating state machine with the same language, and unimplementable if there just exists no such communicating state machine. And this is important for our notion of soundness and completeness. And I want to briefly recap what this means to us here. So for this, I need to show you what I have as algorithm results. So if an algorithm gives you back the tick, it says, oh, in my opinion, this is implementable. And if the algorithm gives you the crosser, it's not implementable. Given that in mind, soundness basically means if I get the tick back, then the protocol should be implementable. So intuitively, all the ticks should only be in the green box, in the green blob, and none of the ticks should happen for the global types that are outside of the green blob, right? If you think about completeness, it actually is here the opposite statement. If it's implementable, then it should actually also give you the tick, your algorithm. So intuitively, you can have all the crosses in the blue part, but you should never get a cross in the green part. So if we say that we have a sound and complete MST projection operator, the overall picture looks like this. We get the ticks in the green part, no crosses in the green part, only crosses in the blue part, and no ticks in the blue part. And this is exactly what I talk about. And I added an example because, Marco, you said something that I kind of disagree with a bit. You said that if you have two participants who are part of a choice, then any other participant should be notified later on. I agree with the notified part, but I do not agree that you need to have one specific message. Here in this example, A and B, again, take the decision. Like A takes the decision and B knows about it because of the message it receives, right? Like at this point, B knows, okay, if the message is orange from A, we took the left branch. If the message is purple, we took the right branch. Later on, in this loop, C receives two orange messages from B all the time. The difference here is in the first two blocks. Here, C receives one orange message, while in the right part, it does not receive any orange message. So at the end, once the blue messages arrive, which just indicate we're done with the protocol execution, and C should know which branch to take, the parity of the messages, of the orange messages, actually lets C know which branch was taken initially. It doesn't learn about it just by one specific message, but because of the semantic property of all the messages that appeared before. Okay, we can handle this, but I want to give you some more details on our setting. So I talked about asynchrony, and then we also know, most of you know about directed choice probably. This means if you branch, you have a dedicated sender-receiver pair, and only the messages need to be distinct and can be distinct. We consider what we call a sender-driven choice setting, where we only fix the sender, here A, and the pair of receiver and message need to be distinct across all branches. So intuitively, this means that you're allowed to send to different receivers, obviously, but if you flip that, it also means you should be able to receive from different senders. This comes with its own challenges, and this was actually what I will talk about in like 10 seconds probably. I enlarged here the blob of implementable protocols a bit. From my discussion about the soundness, what you intuitively want to achieve with the algorithm is to cover all this green space. So let me start with, and I know this is by no extent a full list, because I just said, okay, the first paper on multi-party session types proposed the projection operator, which is linear and considers directed choice. There have been multiple more papers later going from plain merge to full merging, but I don't have time to list all of them. What I want to say is that we basically start from this, and obviously this is a qualitative view, not a quantitative view that there's so much space around there, but I need space for my labels here. So with our Conquer work in 21, we extended from a linear to polynomial complexity to go to a sender-driven choice setting. And why do we need polynomial complexity here? Because this receiving from different senders comes with its own challenges. If I receive in the directed choice setting from one single sender every time I branch, I can rely on that FIFO order for that channel. But if I receive from two different senders, then these messages are not necessarily FIFO ordered. There is a partial order between these two channels. So I need to, we came up with this idea of a message availability analysis to account for these races and check if they're detrimental to learning about the choice. So this is the cost you got with polynomial, and it's cubic, so it's not like to the 10 or something. And we've implemented that back then. It works nicely, and it's the overhead is lazy in the sense if you don't need the computation, you don't need to pay for it. Okay, but still, this doesn't cover everything, right? So in eCoop this year, I presented an XSpace decision procedure for almost the full class of global types. Almost, because I require for every infinite execution of the protocol that every finite prefix of it can be completed to a finite completed run of the protocol. That's a side condition that I needed to show a reduction from MST implementability to high-level message sequence chart implementability. Still, this was not fully complete, so this is what we covered with a direct MST projection operator, and we also settled the complexity to be PSPACE-complete. And this is exactly what I want to talk about here in more detail. So our approach consists of two phases. The first is we construct a candidate implementation, which is very similar to the first few slides I've shown you. You just take the global type and you just project it onto the alphabet of the participant you consider. I'll go into details. And then the second part is we have annotations on these candidate implementations that allow us to check two conditions. We call send and receive validity. And we've proven both of them together to be sufficient for implementability and each of them to be necessary, giving you completeness. So the first phase has two steps. Step A, we translate this high-level message sequence chart or global type into an automaton. And we label the states, which you can think of the global points of the protocol you could be in. And then the second point is you take this automaton and you project it onto the alphabet here of the client. So this is the load balancing protocol from before, I should have said. And you see that the first interaction projects to S!T because the client sends the task to the server, while for the next two, like these two, the client is not involved at all, so this is an epsilon transition. The subsequent ones are just receive parts, and the error spec are again for readability. So now we keep track of these local points and we determinize the result. So you just do a determinization and you keep these labels of the global points in the protocol you could have been in. And intuitively this means that if I'm in this state as the client C, then my local view is compliant with any of these global states 2, 3, or 5. And these annotations we use in order to check these two conditions, send and receive validity, which are the second step. So first I want to give you an intuition what send validity means. Here we have an unimplementable protocol, which is basically the one I've shown you before, where things went wrong, just flipped top and bottom for space reasons. So A decides the branch, but B doesn't tell which branch was taken to C. C should know the branch. So let us construct this candidate implementation for C. You see, okay, at the beginning we're in T1 or B1, then we receive a message, we're in T2 or B2, and then we branch, sending an orange or a purple message, and we are then either in T3 or B3. And this always, as I've shown you before, exposes this execution where C thinks we're in the bottom branch while A and B think we're in the top branch. So that's the reason why we're not implementable. You can fix this protocol, and obviously this is not a fix for the real world, but for illustrative purposes here, by asking C not to know which branch was taken by just sending a blue message in both branches, so it doesn't learn. And then the candidate implementation looks like this. Here, there's one single transition from T2B2 to T3B3, and then the takeaway message for send validity is basically, if I'm in one state with an outgoing send transition, this send transition needs to be possible from every single state that I annotated. Otherwise, we've shown that this can cause problems. For the other operation, so receives, let me also give you a very toy example where, again, A decides the branch to take by sending distinct messages, and then both the subsequent interactions are the same messages, just in different orders. The candidate implementation for C looks like this. Initially, it's in T1 and B1, and then it can receive any of the two messages, and if it receives from A first, it thinks it's in the top branch. No, it should be exactly the other way around. I'm sorry, this is a typo. So, that's unfortunate. Yeah, basically, I don't use the graphics, but I give you the intuition. It branches depending on which message message it receives first, but then it also determines the branch it took because the global, like the per participant order is fixed for the global type. And then this here will always expose the execution where C thinks it's in the top branch while A and B actually decided to be in the bottom branch. This is correct with respect to the left part again. So it's not specified. Intuitively, you can check this, that this confusion arises with these available messages I was talking about earlier. So at this point here, if we can take this receive transition, we should check that no other message is available from the other transitions, because then confusion can arise. So we can again fix this protocol here by introducing extra dependency, where C now actually acknowledges basically the reception of the first message to A here, not to the sender of the message, and then you introduce this dependency, so the message of the other branch that shows you which choice was taken for the other branch will not be available yet. So intuitively, participants learn about earlier choices through receiving, and this is why we need to check that these available messages are unique. So overall, we've shown that these two conditions together are sufficient for implementability. So if you take a global type, you produce the candidate implementations, you check both conditions and they're true, then this candidate implementation actually implements the global type. And for the reverse direction, we showed that if one of the two conditions breaks, there actually is a counterexample to implementability. In terms of complexity, we've shown PSPACE-completeness. The upper bound is basically membership in PSPACE, and with the earlier results, it suffices to say send and receive validity can be checked in PSPACE. And for the lower bound, we use the reduction from NFA universality, which is inspired from earlier results from the early 2000s in the high-level message sequence chart literature. And notably, this result persists for the directed choice setting, so it does not need the sender-driven choice. We evaluated this approach against our own prototype and see that the runtime doubles, but it's pretty much the same order of magnitude despite of this PSPACE hardness result, and we've shown some of the protocols that could not be verified with our earlier prototype to be verifiable. In fact, with the completeness result, this should be true for any protocol that you feed into the prototype. For the proofs, how we do this, there are more details in the paper. And what I do not want to cover here in detail, you know, I've said implementability problem as this deadlock freedom plus same language. But our results actually entail a number of interesting properties that you care about in for your system. So absence of unspecified receptions, absence of orphan messages, that every transition in the communicating state machine is executable, and so on. So to wrap up, I leave you with that visual that shows that we covered with this algorithm the implementable space for the asynchronous and sender-driven multi-party session types and showed this problem to be PSPACE-complete. Thanks.
She already gave to me.
Go ahead.
This is really wonderful and shocking result for me, as I said before. And yes.
I think I could clarify on that a bit.
Yes, and so, but I had, so I think you are, so first cover paper, you use target is communicating automata, right? Mm-hmm. And there were your paper example which cannot be represented by local type syntax. Am I correct? There is a epsilon, you said.
Do you know which example you're talking about?
Not probably, but probably paper you have epsilon, so that, but it from your presentations. Intermediate state is actually only epsilon is using for intermediate state, and
yeah, but that's just an intermediate representation. The candidate implementation, like our state machines.
Because epsilon is not to be able.
But this is the domain. This is just an intermediate state that we use, but our actual candidate implementations do not use epsilon transitions.
Okay, so
yeah, but, I mean, yeah,
okay.
that should work.
Okay, so then which means that your Concur paper actually translated to targeted local type, yes. Right? And but you changed it to communicating automata.
Yes. We felt that this was more natural in this session, for this work. And we actually have an example where at first glance it looks like we produce something that is not representable as a local type, but this is not because of epsilon transition. This is because of some structural properties. Because if you think about local state types, they always have this tree-like structure. But we have ongoing work that shows that this is not a restriction actually.
Okay.
So you can turn these things
to local type syntax.
Yeah.
Okay, I will.
Yeah, but I think.
But your paper said you cannot do local type syntax, but probably I'm misunderstood.
I don't think we claim that, to be honest. I think we claim that the classical projection approach would never produce something like this. But what I just claim now is I can produce this and I can transform it back into a local type.
Okay, thank you.
Which is different. May I clarify on your comment from your talk actually? We do not employ asynchronous subtyping. We don't
yes,
do subtyping.
I know it.
Okay.
I know it.
Because
you don't.
obviously if we did, then this would all be a bit dodgy.
Yes, no. But I found because my work is, project and using subtyping, sound and complete. But your work is only projections, but complete. So not projection, in the case projection, but complete. So I'm very impressed by.
Thanks.
Yes.
Thanks.
I have more questions, but I have other people.
I'm here until Friday.
I saw Ray first. So Ray, go ahead.
Thanks. Sorry, no, just a very simple question. Probably I just missed it. Are there any restrictions on the protocol for your approach to work at all? Is it completely free form? Anything?
Sender-driven choice.
Sender-driven. Okay, so
that's a restriction we cannot get around with this approach currently.
Okay, right.
That's definitely one. But I would say it's already a generalization to the directed choice that is normally considered.
Okay, sorry, and just
so no mixed choice. That's
Okay, so
to be very explicit.
no mixed choice, the sender-driven choice, but that one was two properties sort of rolled in. No, well, there's two sides to that, right? The sender-driven choice. There was.
Yeah, let me.
Sorry, I just missed a little bit.
No, that's fine. I can tell you that. I mean, we say sender-driven choice for the global types, right? We do not put restrictions on the communicating state machines, though. In fact, our completeness result shows, because of send validity, a corollary is that you don't need mixed choice states, which usually is an assumption in MST frameworks, but we show that this is actually a reasonable assumption. So if you take any protocol which satisfies sender-driven choice, you can always implement it without mixed choice states.
Okay, and sorry.
No, that's fine.
And your approach verifies the sender-driven choice. It doesn't just assume this.
I mean, this is just a structural property.
So it's a very trivial.
The prototype, I admit, does not check this, but it's just take the syntax, and for every choice, you check that the sender is the same and that the message receiver pair are distinct. I would say that's pretty easy pre-processing. It's a structural property. It's not like something. I do not say if you give me a mixed choice global type, I do not say there does not exist a sender-driven choice type that actually implements, like specifies the same protocol. That's a different
you start from global types and then you transform them in global automata. Now, does your result only hold for when you start from global types? So actually you can get rid of global types. So you have more, because I believe the automata can be more complex, right, than a global type. And I think maybe also what Nabucco was saying before.
Yeah. So the approach, I mean, it takes the translation, but it doesn't use the fact that it's the image of a global type at all. Yeah.
So it holds for any automata, basically.
Small caveat, every final state needs to be sync, because that's a property of global types that you get always, right? So you do not allow outgoing transitions from a final state. So other than that, any, yes.
Say that again, has to be what?
A sync, no outgoing transitions.
Okay.
Yeah.
So Lorenzo,
I mean, I can ask very quickly. So you said you don't use asynchronous subtyping?
We don't use subtyping at all in this work.
Okay, that you answered.
Yes. We only produce I mean, it's ongoing work.
Okay.
okay. Finally, what thing you have?
Yeah, so thanks for your talk. So there is one point that I think I already asked in the past, where is the status of this notion of, in the syntactic version of global types, so global type is acceptable if it's projectable to every participant. I wonder if this has some status in your setting. So that's my first question. The second question is, can you express delegation because, or this kind of thing that for which we say, okay, it's nice to have a process calculi behind one thing is delegation. So can you comment on that?
Okay, yes. First question I remember, and that we also discussed. I think my answer didn't change much, to be honest. It's just the notion, yes, the notion of what is supposed to work. We do not use the circular argument that you define like the projection and then you say it's fine if the projection works. We say this is what we would like to achieve, which is a communicating state machine for this protocol.
Right.
And then we have this only allows us to talk about our projection operator in relation to this property. Because if you define the property in terms of your definition, it's kind of a bit circular. Second point, again, is ongoing work that I just put into my thesis. So basically using this for type checking and also delegation. And because I just submitted only, and we will put that into submissions very soon.
But the sound is incomplete. So, I mean, where you have to find that doesn't include delegation. Because I was expecting to be expressible somehow with this.
No, this work does not include delegation.
Okay, we better move on to the time. So thank you very much.